So the topic for this video is arrays, and we've already had a couple lessons about arrays, like the tutorial on character strings and those two on heap memory versus stack memory. But there are a lot of things that we haven't talked about, and it definitely deserves its own video. So what else can we say? So if you're making like a short array, like here's length 5, there's the syntax for initializing it using these braces. So this can be convenient if you're writing like a chess program, or maybe you're going to write a program that plays Connect 4 or Scrabble or something, and there are just finitely many things that you need to put into this array. If you're doing science, then you might need like an array with 50,000 entries, and then of course you're not going to initialize it that way. You're going to have to read data from a file or something like that. But this can be useful just for tooling around. We've already said what this is. This AR is, if you refer to it directly, it's a pointer to the memory address at which this stack allocated memory begins. You can, use %p to print that out using printf. But when you use this notation, it's a constant pointer. It can't be changed. And somebody, I didn't even know you could do this, and I haven't Googled it or anything. Maybe you can look into it. So in C, a really common error, and also a source of security problems, is that the arrays don't really know how long they are. And there's a little bit of a caveat to that. Like I've kind of tried to illustrate that in this little program that I've written here. So after I declare this int array of length 5, I ask the size of operator, how many bytes does AR use? And it correctly gives the answer of 20, because each int is 4 bytes, and this has 5 ints, and so 5 times 4 is 20. I have no idea how that works, and I don't really trust it, so I wouldn't use that, and maybe research it on the internet a little bit. Maybe you can tell me something about it. So here I've passed the array to a function, which is something that you frequently want to do, so we should know the syntax for that. We've already really seen that syntax in when you do main. The variables that you have here are arg c, and there's char star arg v. So what is that? That's a pointer to it's an array. What is it? It's it's an array of char stars. Yeah, so it's an array of strings. But if you want to just pass, and each string is itself an array, so it's almost like a 2D array, right? But here you're just passing a one-dimensional array. There are a couple ways to do that. Notice that if once we get to this function, however it was, the system was remembering or knowing that 20 bytes were allocated to AR. It's totally forgotten it by the time it gets up here to this function. It's another reason maybe not to trust that too much. And so I'm experimenting a little bit here. What do you think would happen if down here I printed out using %p? Here, let me just do what I'm talking about. Down here, if I print out %p, and I look at AR as a pointer, and then I do the same thing up here, they're going to be the same numbers. So what's the address in foo? It's going to be the same as the address in main, right? And let's just run it and confirm that that's true. Oh, AR. I called it something different up here. Right. So the address in main is this. The address in the function is the same. In fact, that's exactly what gets passed to the function, is the address, and it gets put into array here. And so I've done a little test here to see if this worked, because if you've been watching the previous tutorials closely, you might remember that when you declare an array like this, you can't do AR++ for pointer hopping. It'll explode and yell at you, right? So there's the error. It says L value required, whatever. But up here it seems to be much more pointer-like, and in fact there is another notation that you can use for passing a one-dimensional array to a function. If you compare this output to the previous output, you'll see that it's exactly the same, except of course the address has changed because it's randomly assigned every time. Um, yeah, so those are some important things. I just wanted to talk about those. So these are arrays that are allocated off the stack. You can allocate them, of course, off the heap too by doing dynamic memory allocation. So how could you do that? You could do int star ar equals malloc 5 times size of int. So now I've got enough memory off the heap for 5 integers, just like before. Now you can't use that notation that I used before for initializing them. So let me just put AR0 equals 2 and just leave it at that, right? And just to help build good habits, let's remember that we have to give back the memory when we dynamically allocate it. And oh, sorry, you have to include standard lib or it yells at you when you use malloc. Include standard lib.h. Right. And right. So this is interesting. So when you get the memory off of the heap, it seems to not have the ability to determine how many bytes are allocated to the array like it magically did when I used the other notation. Like I said before, I have no idea how that works. But otherwise things are exactly the same. And maybe I forgot to mention this before. Just as an experiment here, I changed the 0th entry to be -1. Before it was 2, right? But down here, the last line in main, if you look to see what's there, the values in the array were changed, and that's because the address gets put here, and what you're basically doing is, this is really the same thing as just dereferencing the array, right? And if you wanted to put something, I think I talk about this in the tutorial called pointers, which is the second tutorial. Now if I dereference array again and put in -2, and down here just to illustrate that something's changing, let's put +4 in there, and then let's just copy this and do an experiment to see what's in the first place. It's going to be the changed value. So, and I'm doing this because you really can't see pointer hopping too many times because it's a little bit confusing, right? Do you understand why this does the same thing as referencing the first element? It's because I'm treating it like a pointer. Actually, it's a pointer to this memory address, and then if I increment it, it goes up by 4 bytes to the entry for the next int, and that's why this pointer hopping approach does the same thing as using the subscript notation. Now let's do something that you might actually need to do with an array. So like some things that you frequently need to do with an array are, let's say, find the index of a specific element. So in Python there's even a command for this, isn't there? It's like index or something like that. So let's write a function that does that. So let me put this back, and by fooling around like this, I'm going to end up with a video that's longer than necessary, but and then nobody will watch it. But let's try to write a function, the index function, and I'll define it up here, index, and what we're going to do is we're going to return the index of a specified element, and so that's what this function is going to do. Of course, that element might not be there at all, and we'll return -1 on failure. The case in which the element that is being sought is not there. So we're looking for an int, and so we'll call that sought. Now you need something else here, which in Python you wouldn't need, which is the length of this thing. So we've proved that index, the function, has no freaking idea how long the array is, and so that's a kind of a problem with C, but that's what you get in exchange for all the good properties that C has, I guess. So I'm going to put in a value for the length also. And now let's call the function. So printf the index of 3 is, and now let's use the index function that we just wrote to find it. So it's the index in the array R of 3, and the length of AR is 5. Okay. Now we have to actually make the function do those things, and this is something that you do just 1,000 million times after you start writing a lot of C or C++ code. You use a for loop to look through a one-dimensional array. So we're going to go from 0 up to the length of the thing, and we'll increment each time. You need your braces, you need your indentation, and we'll say if, what should we say? If array I is the thing that's being sought, then we will, there's several things we could do. I could put in a return statement right there, but that's not necessarily a good style. So let me do something a little bit different. I will, let's make a Boolean value that records whether or not it was true. So this is how you do a bool in C, and this is a value that's either true or false. And let's call this was found. And let's say the presumption was that it was not found. So now if this condition holds, then the thing was found. So I'll do was found. You just have to put in some non-zero value, like 1 is a good one. And then we found it, so there's no sense in going the rest of the way through. So we'll just immediately exit the repeat loop. And down here we'll say if was found, then we should return I, and else we'll return -1, because that's what we're supposed to return on failure. So we still have two return statements, but they're both at the end of the function. You want to be careful with putting a lot of multiple returns into your functions. On the other hand, you don't want to be pedantic. There are some cases in which it makes things a lot more simple. Alright, so I have to say that the function is going to return an int. And there's a warning: conflicting types for built-in function index. So I'm not sure what it's talking about. It says there's an error on the 7th line. And what if I change this to an uppercase I? It might just be that there's some, built-in C function called index, and in fact that's what was happening. And so the index of 3 is 2. Is that correct? 0, 1, 2. Yes, that's true. And let's make this a little bit more general here. Let's try to find the index of 1. Okay. So the index of 1 is 0. Is that right? Yes, it's right. So that's something that you might want to do with an array. There are lots of other things, like common things are sorting an array, finding the maximum element of an array. Let's do that one. Find the maximum. I wish I hadn't erased that. Let's just leave that there, and I'll write a brand new function. A function to find the index of the maximum element of an array. Okay, so common task. And so we'll do int and call it something maxi, because max might have that same built-in problem that we had before. And we still need basically, maybe not all those things, but a lot of those things. And okay, so we're not looking for any particular thing. So we'll just take the array and the length. And so what we're going to return is the index of the maximum element. You can see that the answer in this case is going to be 4. But let's assume that index of best, that's what we're going to return. We've got to start it somewhere. So let's suppose that the index of the best is 0, and then we'll increment it if necessary. And let's have another variable which is best seen so far, and let's make that equal to the 0th entry of the array. And so we need to check a condition here, which is maybe the array is only one element long. That would be silly, but you never know what kind of stupid crap people are going to do. And if len equals 1, then just return 0. Okay, maybe I should even, my code would be slightly more clear if I just did that first. Okay, so if the len is 1, then just return, actually this should be array 0. So if there's only one thing in the array, then no, sorry, it is confusing the difference between the value and the index, right? So return the 0 will be the index of the maximum element if there's only one thing in the stupid thing. And otherwise, we need to start some kind of for loop. So let's do the for loop thing that we always do. I is less than the length I plus plus, and we'll see. We need to check and see if the one that we're currently looking at, there's no reason to reconsider the 0th one. We've already considered that one. And we also can assume that if we reference the 1th, what I mean is if we type in that, it's not going to give us a segmentation fault, which it very well could if the length of the array was 1. Running off the end of an array is something that you're going to do over and over and over again, and when that happens it causes a segmentation fault. But we won't get a segmentation fault in this case by talking about the 1th, because we've already checked for that condition, so we're safe. And we should check to see if this value is bigger than the best the best value seen so far. So if it is bigger, then let's make the best seen so far be equal to this new thing, which is bigger. And then we also need to update the index of the best, which is now I. And all we have to do is return index of best, and that's the end of the function. So let's put in another print statement to test our function. If you never test, code is always wrong the first time you write it, and you have to test it over and over again. Index of best, or biggest, is blah blah blah. And so what do we want? We want the index, and so here's where I reference my function, which I called maxi. And I passed to maxi, oh, this is nice, Genie is a great little program. So you give it the array and you give it the length, which is 5, and now we're good to go. And the index of the biggest is 4, which is true, because this 5 is in the 4th place. Let's change that to 30. Then the index of the biggest is 2. 0, 1, 2. Works. There's some, maybe you could test that more thoroughly, but I'm convinced. And I did make a function here with 2 return statements. I frequently do that if there's some error checking that you do, some simple error checking at the top of the function. Frequently you have to do that. And then I kind of forgive myself for multiple return statements. And that's pretty much it. I'm going to stop the video.